Welcome to lecture 12, NPTEL online certification course on bioreactors. In the last lecture, we had solved one of the practice problems. In this lecture, number 12, let us continue the module 3, which is on analysis of the common bioreactor operation modes. In the earlier lecture, we saw the batch mode. In this lecture, we will see the continuous mode. And as mentioned earlier, the continuous stirred tank bioreactor is also called the chemostat. Very common term used for the continuous stirred tank bioreactor. So we will look at growth in a chemostat. This is the representation of a continuous stirred tank bioreactor or a chemostat. You have the stirred tank, this is the stirrer, this is the vessel here, this is the broth or the liquid in which the cells are growing. The cells are actually blown up. You won't be able to see the cells as individual cells normally. We have various measurement probes, probably the DO, the pH and the temperature probes, and we have aeration, assuming that this is an aerobic bioreactor. Then there is a continuous stream of input and a continuous stream of output, right? And let us say that the feed rate, the volumetric feed rate, volume per time at the inlet is Fi, the substrate concentration in the feed is Si, and the cell concentration in the feed is Xi. The same parameters in the outlet of the bioreactor, F naught or FO, let us say, FO is the outlet feed rate, volumetric feed rate, volume per time. The S is the substrate concentration here, and X is the cell concentration here. And the volume of the broth, which we will take as a system, is V. As you can see, a part of this is being pulled out. So the substrate concentration and the cell concentration here need to be the same as in the outlet stream, because what is being inside, well mixed, is being pulled out. Okay? Therefore, the concentrations of these two would be the same. Now, let us define something called a dilution rate as the volumetric feed rate divided by the volume of the broth, F by V. This is a definition, dilution rate. So, can you make sense of this? A certain feed rate divided by the volume. So, if you visualize it as certain feed rate divided by the volume, the dilution rate can be interpreted as the number of reactor volumes processed per unit time. So, it needs to have a unit of time inverse. Just think about it a little bit, see whether you are comfortable with the interpretation of number of reactor volumes processed per time. Usually, there are no cells that are present in the inlet of the chemostat, and this condition is actually called a sterile feed condition. In the feed, there are no cells, it is sterile, and therefore it is a sterile feed condition. This is the usual mode of operation, unless you are using a chemostat in a different way and so on, maybe attached to another chemostat, attached to another bioreactor. Those are different. Standalone chemostats usually don't have an inlet cell concentration. There's just substrate in the inlet stream. Now, I'd like you to understand this a little better. Usually there is a lot of confusion. When the chemostat starts operation, okay, you have a vessel here, you're starting in a feed here, there is nothing before that, and so on. There will certainly be a difference between the inlet and outlet flows. Okay, we are not denying that. Therefore, till the flows can be adjusted, which will take probably a few hours and so on and so forth, to be the same and the conditions to settle down to the steady state conditions, there will be variations in the inlet and outlet. We are not looking at that period at all. Those are the startup conditions where there will be unsteady state, and there will be shutdown conditions. When you shut down the bioreactor, it needs to be done in an appropriate fashion, and then the process will not be a steady state. If you leave out these two, which could probably be a short duration compared to the overall duration of the chemostat, most of the duration it is going to be at steady state. And we are going to look only at the steady state part of the operation of the chemostat here. Okay, you need to keep this in mind. So this is what is said here. The fraction of total operation time for startup or shutdown is small. We will not consider the startup or shutdown here. We are interested only in the steady state when Fs, F is the volumetric feed rate, S is the substrate concentration at the outlet, inlet, inlet, there's no problem, outlet, X is the cell concentration in the outlet, and the volume of the broth. All these variables do not change with time. This is the condition that we are going to analyze, and which is the condition under which the continuous bioreactor or the chemostat will be in operation for most of its useful period. The objectives of our analysis would be as follows: to obtain the conditions for steady state operation, to obtain critical dilution rate, the maximum operable dilution rate, to obtain an expression for cell productivity in a chemostat and compare it with the batch bioreactor productivity. You might be in for a good amount of surprise here. Okay, let's begin the analysis. This is the same chemostat as was shown earlier. The inlet at Fi, Si, Xi, usually Xi is 0, and the outlet at F0, the volumetric flow rate. S and X are the substrate and cell concentrations respectively. Here the volume of the broth is V, which is also the system that we have chosen, indicated by these dotted and dashed lines, and S and X are the same as in the outlet. System as shown. Let us do a balance on the total mass. One of the huge tools that we have is mass balance. So this is the mass balance that by now we should be familiar with: rate of input minus rate of output plus the rate of generation minus rate of consumption equals the rate of accumulation of mass. We are doing it on total mass. Since we are doing it on total mass, there can be no generation, there can be no consumption. Total mass is always conserved. Therefore, only input and output. And we said that we are interested only in the steady state condition. If we are interested only in the steady state condition, any time derivative can be blindly set to 0, right? So this term goes to 0 by the definition of a steady state. Therefore, rate of input must equal the rate of output. This is total mass. What is rate of input in terms of our volumetric flow rate? A volumetric flow rate is volume per time. We are looking at mass per time here. Therefore, if we multiply the volumetric flow rate by the density, we would get our mass rate. Therefore, Fi into rho I is the density of the incoming stream, fluid density, equals Fo times rho O, which is the feed rate and the density of the outgoing stream. Rho is the fluid density, as we mentioned. Usually, there is no difference in densities between this stream and this stream. We are operating at room temperature, at standard conditions, maybe 30 degrees, 37 degrees C, 1 atmosphere pressure. It's not easy to get a difference in densities between these two streams under those conditions and given the contents of the system. Therefore, rho I and rho O can be cancelled out. Fi needs to be equal to Fo, and let us say that is F. Okay. So through a mass balance, we got that the flow rates need to be equal. Now let us do a mass balance on cells over the same system. Earlier it was total mass balance. Now we are going to do a mass balance on cells. This is the original equation. There is no input on cells. It's a sterile feed, right, into the system. Therefore, Ri is 0. There is no consumption of cells. There is no death of cells. We will assume that. So Rc goes to 0. and steady state, any time derivative goes to 0, therefore this is 0. Therefore, we get RO equals Rg, minus RO plus Rg equals 0. Therefore, the rate of output must equal the rate of generation of cells. What is rate of output? The volumetric flow rate times the cell concentration. You work this out in terms of units. You will find that this is indeed mass of cells in the outlet stream, with the mass rate of cells in the outlet stream, times the rate of generation, which is mu x into V. Mu x is the rate of generation of cells per unit volume on a volumetric basis. We need to multiply it by the volume to get on a mass basis. So, Fx equals mu x times V. So, if we transpose this equation and take x common out, we will get mu minus F by V equals x. You can see this. Mu x V minus Fx equals 0. So, you take x common out and divide it by V. So, here you have only mu left, here you have F by V times x, so that equals 0. So, if the product of these two terms equals 0, then that is possible only if any of these terms is 0 or if both the terms are 0, right. So, and before that, let us replace F by V with our definition of that. We called it the dilution rate, remember, the number of volumes processed, reactor volumes processed per unit time. So, that we will replace first and then analyze. So, mu minus D times x equals 0, and so either this term is 0, which means mu equals D, or x is 0. Okay, only under those conditions will the equation be valid. Now, let us look at these two conditions. When there are no, what does x equals 0 mean? X is what? That's a cell concentration in the outlet stream. When x equals 0 means there are no cells coming out in the outlet stream, okay, which is what is called a washout condition. It can actually happen in the case of a chemostat operation. There might be no cells that are coming out, and the reactor could be at steady state even under those conditions. But it's a useless condition. We will not be able to operate effectively under those conditions. It's non-productive having no cells in the outlet. So, but this is a condition for steady state. This is actually called the washout condition. Now, if you look at this mu equals D, it says something very profound. Although it's a very simple equation here, it says that the dilution rate determines the growth rate. Okay, that is very profound, because what is dilution rate? It is F by V. How do we change the dilution rate for a given reactor? For a given reactor, the volume is fixed just by changing the flow rate. The flow rate is under our control. We change the flow rate of the pump, the flow rate will change. So, just by changing the flow rate, we are able to change the specific growth rate. The specific growth rate, as you know, is a biological parameter, right? So, by changing an operational parameter, which is the dilution rate, by tweaking a knob, we are able to have a control over the growth rate of the organism, which is a biological parameter. Okay, that is something very, very profound here. So, an operational parameter f for a given V determines a biological parameter. That's the significance of this equation. So, that will happen under steady state conditions of operation of a chemostat. So, if you want the cells to grow at a higher rate, you just have to increase the flow rate, and the cells will grow at a higher rate until a certain point. We will see that. We did total mass, we did cells. Now, let us do a mass balance on the substrate over the same system. Same balance total, the complete balance equation here. We are going to focus on the substrate. There is an input, there is an output, of course, of the substrate in these two streams. There is no generation of substrate. There, of course, is a consumption, and there is no accumulation because it is at steady state. All the time derivatives are 0. Let us recall that yxs is the amount of cells produced divided by the amount of substrate consumed. Why are we doing this? This and this are straightforward. The input rate we can write in terms of the flow rate and the substrate concentration in the feed. This is the flow rate and the substrate concentration at the outlet. Whereas here we don't really have a handle on the growth rate, on the consumption rate of the substrate. Whereas we have a handle on the growth rate of cells. Okay, so we are using something to represent the consumption rate of the substrate in terms of the growth rate, and we all know, we have already used this in a problem. The yield coefficient yx/s can do that. Let us see how we can do that. So the rate of substrate consumption is nothing but the rate of cell production divided by y-axis. You know what y-axis is? Amount of cells produced by amount of substrate consumed. We are looking at rate of substrate consumed. So let us say we divide by time above and below, we get rate of cells produced by rate of substrate consumed. Take it to the other side, the rate of substrate consumed is rate of cells produced by y-axis. That is what is given here. Now what is rate of cell production? It is mu x into V, right? The mass production of cells. This is the volumetric production rate times V divided by yx/s. So the mass balance on the substrate becomes, the input is F times SI. You know, we, to the total mass balance, we derived that Fi equals F naught equals, say, F. So F times SI minus F times S in the outlet minus mu xV divided by y-axis, this equals 0. Right? So if we consolidate the terms appropriately, if we have here F into Si minus S is mu xV by y-axis, then we divide both sides by V, we get F by V, Si minus S equals mu x by y-axis. So F by V is nothing but D into Si minus S is mu xs by y-axis. Since mu equals D at steady state, and we consider the effect of S on mu m S by Ks plus S, which is actually mu, can be equated to D here. Therefore, mu m S equals D into Ks plus S. This is transposing the equation, multiplying both sides by Ks plus S. Consolidating the terms in terms of S, you know, you have a mu m S here and a ds here. Bring it to the same side or subtract dks from both sides. You get S into mu m minus D equals dks here, and therefore S equals dks by mu m minus D. Okay. So we have S here and X here. We are trying to get it all in terms of S so that we can solve for S. So y-axis is amount of cells produced by amount of substrate consumed. Amount xv is not, the amount of substrate is S naught minus S, Si inlet, right? Yeah, inlet minus S into V. The volumes are the same, we can cancel them. We get X by Si minus S. So X equals the yield coefficient times Xi minus S from this equation. And S in terms of the other parameters is dks by mu m minus D. That is what we derived earlier. Therefore, X equals yxs times Si minus dks by mu m minus D. This is just algebra. Let's go through it. Although it seems like a lot of steps, let's go through it. We are arriving at some interesting place. When the washout occurs, X tends to 0, and there should be no change in substrate concentration from the inlet because it is not being consumed for the production of cells. Maybe a little bit is taken up for maintenance, but that may not be very apparent. Let the dilution rate at which washout occurs be dc. Now, while we are going through all these things, let us also recall why we are doing these things. We are looking at conditions for the steady state operation. Right. Our analysis, objectives of our analysis where to obtain conditions for steady state operation, to obtain the critical dilution rate, the maximum operable dilution rate. That is what we are looking at now through a lot of algebra. When you're doing the algebra, it's good not to lose sight of this. Okay, that's why we need to remind ourselves as to what we are doing. Now let's get back. Yes, we were here. Let the dilution rate at which washout occurs be dC, or the critical dilution rate. From the Monod model, mu m into SI by Ks plus Si must be equal to dC, because at dC S tends to Si, the concentration in the inlet stream. Therefore, we are replacing S with Si. Mu m Si by Ks plus Si is dC, and if we plot the outlet concentration versus the dilution rate, it is, which is this expression. We are plotting the outlet concentration of cells, which is given by this equation. If we convert this into a graph, it is going to look something like this. Something like this. It's actually the drop is very steep here, closer to the DC. At the critical dilution rate, actually there are no cells that are present in the outlet. The cell concentration is 0. And from the expression that we derived, S equals dKs by mu m minus d, the substrate concentration, that goes something like this. It reaches the substrate concentration in the inlet at the critical dilution rate. So this is the range at which you can operate a chemostat. After critical dilution rate, there will be washout, there will be no cells, and there will be no conversion of the substrate. There is no point in operating the chemostat there. Now to the third objective. If you recall, we were going to compare the cell productivities of the chemostat with that of a batch bioreactor. To do that, let us see what the cell productivities are. Our interest is to, usually general interest from an industry is to produce the maximum amount in the minimum possible time, right? The productivity is actually defined for that purpose. It is the amount produced per unit volume per unit time. In a chemostat, the cell productivity is therefore the amount of cells produced per unit volume per unit time, if these cells happen to be the product. Even otherwise, if the cells are producing a product, we would also like to maximize the cell productivity, because that would directly translate to the increase in production of the molecule inside the cell, right? More the number of factories, more the product of interest too. Therefore, we are looking at cells themselves. If we represent the chemostat productivity by R of a chemostat, it would be the cells produced per unit volume is X, 1 by time is mu, therefore X into mu, that would be X into D. And graphically, X was like this, the cell concentration variation with D was this. We have already seen this. The productivity will go something like this. The productivity will go on increasing, going by the earlier equation here, X into D. X into this thing was like this. So it goes on increasing till it reaches a maximum productivity at dm, and then it will actually drop till the point of the critical dilution rate where it becomes 0. There are no cells coming out, so the productivity needs to be 0 there. So this is a graph of X versus D that we saw earlier, and now we are seeing a graph of R versus D on the same axis here, on the same D axis here. Let us find out the dilution rate dm at which the cell productivity R is maximum. Okay, we'll call that dm. We are interested in maximum productivity. Let's compare maximum productivity is possible. For a function, we know the conditions for a maximum, right, mathematically. What are the conditions? For example, if R equals f of d, at the maxima, at the maximum point, dr dd would be equal to 0, or d by dd of r would be equal to 0, the maximum, the slope becomes 0, and the second derivative would be less than 0. That is the condition for a maxima. Alternately, the condition for a minima is that dr dd would be 0 and the second derivative would be greater than 0. Okay, this we all know from our initial math courses. Here r is nothing but dx, which can be written in terms of the other variables as d times xs, the yield times the substrate concentration, therefore yxs times Si minus dKs by mu m minus d. If we expand, we will get d times yxs times Si, first term, minus yxs dd d squared Ks by mu m minus d, and therefore dr dd, the derivative of r with respect to d, would be like this. The first term is quite straightforward, the d would drop out, yxs Si remain, they are not functions of d. And the second term, you have a d in the numerator and the d in the denominator, and if you take yxs common out here, you can use this a by b form, denominator into derivative of the numerator function minus the numerator into derivative of the denominator function divided by the denominator function squared. So the denominator is mu m minus d, the derivative of d squared Ks is dKs, which is here, and then minus the numerator is d squared Ks, the denominator derivative is just minus 1 here, this term would drop out, minus d, the derivative with respect to d is minus 1, and divided by the denominator squared, mu m minus d squared, that equals 0. Therefore, we get yxs Si minus yxs, this is just grouping the terms appropriately, mu m dKs, which is the first term, minus d squared Ks plus d squared Ks, these two are going to drop out, times mu m minus d squared equals 0, and that is what we have here. This is just transposed to take the other term, one term to the other side. Now we can cancel out the yxs and again represent it appropriately, multiply both sides by mu m minus d squared, we get this, then we get the semblance of a quadratic equation, and d mu m dKs by Si, right, equals, if you expand this, a minus b squared is a squared minus 2ab plus b squared, which is this, and I am trying to write this in terms of an explicit quadratic expression in terms of d. Therefore, d squared, I am just bringing this term to this side, t squared minus 2 mu m minus Ks, we will go out here, Ks by Si, which is here, you have a minus here, so that takes care of it, plus mu m squared equals 0. And if you solve this differential equation, this algebraic quadratic equation, okay, it will involve a lot of algebra. If you recall, the solution is minus b, b is what, and this is a quadratic expression in d, therefore a is 1 here, the coefficient of d squared, the coefficient of d, which is b, is mu m into Ks plus by Si plus 2, and c happens to be 1, mu m squared here. Therefore, the solution is minus b plus or minus b squared square root of b squared minus 4ac by 2a. If you do that, you will get this, right. This is dm, or the dilution rate at which the productivity will be maximum. You need also check that the second derivative is greater than 0. Okay, I'd let you do that. There's a lot of algebra. It will take you close to half an hour plus. So we are not going to do that explicitly here. dm equals mu m times 1 minus Ks by Ks plus Si, this whole thing raised to the power of 0.5, the square root of this, that is. Okay. Okay. This is what I said. To ensure that's a maximum, not a minimum, we actually need to check whether the second derivative is less than 0. If you see here, the Ks plus Si, in this case Ks is much less than Si, so I can replace this with Si, Again, if you consider the numerator by denominator, Ks is much less than Si. Therefore, or in other words, the denominator is much larger than the numerator. Therefore, this term actually is tending to 0. Okay, that's what is meant by here. Ks by Ks plus Si is 0. And therefore, when this term goes to 0, dm is approximately equal to mu m, or it is approaching mu m here. Now let us look at the cell concentration at dm. If xm is the cell concentration obtained when the cell productivity is maximum, then we can get an expression for xm by substituting the relevant variables in the equation, right? The corresponding variables, if you substitute in the expression for xm, we should get the appropriate expression. We know that xm is the cell concentration at the maximum productivity. So all the other variables should also correspond to the maximum productivity variables. So d should actually be dm here. The rest are the same. Y-axis times Si, the inlet concentration, so that there is no change here. D has become dm here, Ks is a constant, mu m is a constant, and d has become dm here. So substituting the expression for dm into the above, we get, don't worry about this, this is just dm being replaced in terms of the Ks and Si, that's all, nothing else. So 1 minus Ks by Ks plus Si to the power of 0.5 into mu m, that is what we've seen, that is what has been substituted here for dm. So this is y-axis, Si minus dm times Ks by mu m minus the same dm here. So this is the expression for the maximum cell concentration. This can be simplified. The first few steps are shown here. This is the starting expression, and if I, for simplicity, if I take A to represent Ks by Ks plus Si to the power of 0.5, I am showing these steps because I can quickly show them to you, not like the other derivations which would take a long time. That's the reason why I am putting in the steps here. And therefore, you could write this as just the right hand side alone. I am taking a look at y-axis Si minus 1 minus A into Ks divided by 1 divided by this 1 and 1 would get cancelled out if I open the brackets, and then this would become plus, which would just be A. The mu m and mu m are going to get cancelled out anyway, so that goes out. And therefore, if we take a common denominator here, we are going to get ASI minus Ks, expanding the bracket here, plus AKS, and then combining the terms. Now you are closer to the solution. You need to follow this to a few steps till we get xm equals y-axis into Si plus Ks minus the square root of Ks by Ks into Ks plus Si. Okay, this is the final expression for Km. We can, I've just written this in terms of Ks plus Si outside as common, y-axis into Ks plus Si into 1 minus Ks by Ks plus Si to the power of 0.5. Okay, this is the expression for the maximum cell concentration. Now, when Ks is much less than Si, we saw that this term tends to 0, the denominator can be replaced with Si, and after doing that we see that the denominator is much larger than the numerator, therefore it will tend to 0. So in such a case, if this tends to 0 and this can be replaced with Si, xm would be directly y-axis times Si. And the productivity Rm would be dm times xm. Okay, that's our definition of productivity that we saw earlier. And dm is mu m, therefore we have replaced it with mu m. Xm would be y-axis times Si, so that would be mu m by xs times Si. Let us look at some typical values to get an idea of the productivities here. For yeast, the maximum specific growth rate typically is about 0.5 hour inverse. the yield coefficient XS is 0.5. So if the inlet substrate concentration is 50 gram per liter, the productivity that we can calculate even under these conditions, the maximum productivity mu m y xs SI would be 12.5 gram per liter per hour. You can do the calculation here, the maximum productivity calculation for yeast. If they happen to be mammalian cells, the typical specific growth rates are an order of magnitude less, 0.05 R inverse. The yield coefficient is 0.1. Let's say, this has been done for a hybridoma, which is anaerobic, so it's taken as 0.1. And for an inlet substrate concentration of 5 gram per liter, which is the usual one, the productivity is 0.025 gram per liter per hour. This has to be a superscript, not a subscript. 0.025 gram per liter per hour. So here you get 12.5 gram per liter per hour as a typical productivity in yeast, and here you can only expect 0.025 gram per liter per hour. You see the change in the magnitudes. Now let us compare productivities. Continuous versus batch. Let us take the maximum possible productivity in each case and let us see what the ratio is turning out to be. For the batch, we know the maximum possible cell concentration is SI times y-axis. Time for the batch is 1 by mu ln of xm by x naught plus t naught. When we assume that Ks is much less than S, assuming no lag phase further, we get 1 by mu m ln of xm by x naught. Here I have just replaced mu with mu m, saying when Ks is much less than S, then you would be at the maximum specific growth rate, the asymptotic value. So I have replaced mu with mu m. So 1 by mu m ln of xm by x naught plus t naught. And if we assume no lag phase, it starts growing right from the beginning, which happens many times. Then we can completely ignore the lag time here. And so 1 by mu m ln of xm by x naught. I am doing all this to get an idea of the ratio of productivities. If the lag time is significant, you can always add that for comparison. I am trying to do that on a generic basis, so I am taking the simplest case that is possible, but which is still representative. So the productivity of batch is the maximum possible cell concentration SI y-axis divided by the time that it takes for the batch. The amount produced per unit volume per unit time is the productivity that we define. Therefore, SI y-axis divided by 1 by mu m ln of xm by x0. This is the productivity expression for a batch, starting from x0 going up to xm. Now for the chemostat case, we have already seen that the maximum productivity is mu m y-axis times SI. Therefore, the ratio of the maximum productivities of a chemostat to that of batch is just a division of those two terms. Mu m y-axis SI is that for a chemostat, SI y-axis by 1 by mu m ln of xm by x0. This is what we saw for a batch. As you can see, all these terms cancel out. SI y-axis, mu m cancels out, and then we are left with log of xm by x0. Okay, very nice, simple expression we have. Typically, in a batch situation, you have the maximum cell concentration being about 10 to 30 fold the initial cell concentration. That's what usually happens in a batch. Therefore, the log of this range of values of xm by x naught would be 3 to 4. Therefore, the ratio of the maximum productivities of a chemostat to that of a batch is 3 to 4. And what does this say? Inherently, the chemostat is 3 to 4 times more productive than a batch reactor, right? So this is by the very nature of it. This is also a very profound kind of an insight that we get from this analysis. The chemostat is 3 to 4 times more productive than a batch, usually speaking. Okay. So an industry can expect to be 3 to 4 times more productive by switching to a continuous operation, but operating in a continuous mode requires a lot more effort than operating in a batch mode. That's the reason why industries prefer batch, except if it is completely automated and so on and so forth. Then some industries have switched to continuous. You might want to internalize this by going through this again. We have shown that a continuous bioreactor is inherently 3 to 4 times more productive than a batch bioreactor. Let's see a practice problem. I'll assign this problem and solve it in the next lecture. We will continue after this problem also, the fed batch operation, which I would like to complete as a part of this particular lecture itself. The practice problem reads as follows. Processed fungi are good biosorbents for toxic trace metals, and thus they can be used to remove chromium, mercury, cobalt and other heavy metals from industry effluents. A suitable fungus needs to be produced at 500 gram per hour for the above purpose. The growth limiting substrate concentration at the inlet of a chemostat to produce fungus is 50 gram per liter. The fungus follows monod kinetics and the maximum specific growth rate is 0.5 hour inverse. The substrate concentration that corresponds to the half maximal growth rate is 1 gram per liter. It is aerobic growth with a cell yield coefficient from substrate of 0.5. Find the minimum size of a chemostat needed for the above for a given inlet volumetric flow rate. Okay. So why don't you try this out? We'll of course see the solution in the next lecture. Now let us continue the fed batch operation. How to analyze the fed batch operation? As you recall, fed batch is nothing but intermittent addition, intermittent removal, together or one at a time. All these are fed batch operations. There is a reason for doing the fed batch operation. In fact, that is the most common mode in an industry. We've already seen that the fed batch operation is preferred under some conditions, such as minimizing the deleterious effect of a metabolite formed during the cultivation, or when some special feed strategies need to be implemented. This is one of the some situations where one would prefer a fed batch operation. And let us analyze this operation with an aim to obtain the cell concentration at any time t when there is only input. I am just taking one simple case to analyze to just start you on the analysis. It can get a lot more complex. As long as you know the functionality, you will be able to solve. You will be able to get expressions and solve them towards your needs later. So in this case, there is only input, there is no output. Let us say that Fi as a function of t is the volumetric feed rate of the entering stream, and Xi of t is the cell concentration in the entering stream, just for generalization. It's not a sterile feed. And Rx is the cell growth rate on a volumetric basis. If we do a material balance on cells with the bioreactor contents or the bioreactor broth as our system, this is the overall balance equation. There is no output in this case, right? That's our condition, only input, therefore RO is 0. There is no consumption of cells, let us assume this, therefore this is 0. This is not at steady state, so this cannot go to 0. This term still remains. Ri is nothing but Fi as a function of t times Xi as a function of t, and Rg is nothing but Rx times V. You can go and check your previous lecture notes to see that this is indeed the case, equals d into mass is nothing but concentration into volume, cell concentration into volume, d dt of xv. Now we no longer have that niceness of something being constant. All the terms are there. So Fi as a function of t, Xi as a function of t, first term plus Rx into V. Here V is not a constant, right? So x into dV dt plus V into dx dt is the expansion of dxv dt. right? So all these terms are still there. Except this term dV dt, we can handle the rest of the terms. We know the inlet feed rate as a function of time, we know the inlet cell concentration as a function of time, we know a rate of cell formation, and we know the volume of the bioreactor. So this is the only term that we need to handle to get a handle on this equation. To do that, let us try a total mass balance on the bioreactor broth. If we do that, the total mass balance, there is no output, there is no generation of mass, there is no consumption. Okay, all these terms go to 0, and therefore Fi as a function of T into rho I, this is total mass, equals D into rho V, this is total mass again, right? This is density into volume by d dt of rho V. Usually the inlet and outlet densities are the same and a constant, therefore we can take them out of the derivative. Fi T times rho, which is the constant density, equals rho, the constant, so we take it out of the derivative, rho dV dt. So Fi T is dV dt, cancelling rho's both sides. Therefore this equation becomes Fi T xi T plus Rx times V equals x into Fi T plus V into dx dt. So the dV dt we have replaced by Fi T here, right? The rest is the same. Therefore, combining the like terms together, Fi T into xi T minus x, we have brought this to the other side, plus Rx V equals V dx dt. All terms are known here, we can take things forward towards our ends, right? So this is the final expression here, dividing it by the volume Fi T by V, xi T minus x plus Rx x equals d dt of x. If these functionalities are known, then we can solve this to get the cell concentration profile in the bioreactor, in the fed batch bioreactor. I think we will stop here for this module. In fact, we have completed this module on bioreactor analysis, the common modes of operation, the analysis of that. We initially saw the batch bioreactor, analyze the batch bioreactor towards getting some useful estimates, and then we looked at the continuous operation. A problem has been assigned, please do that, and finally we looked briefly at how to handle fed batch operation. Okay, see you in the next lecture, and we will of course first solve the problem in the next lecture.